So let's start to discuss how to build the distributed concurrency primitives. My name is Andrii. I'm from Ukraine and currently working for Hazelcast. It is a platform that allows you to use not only concurrency primitives, but another distributed platform features. Also, I am a professor at National Technical University of Ukraine. Java is a group leader of Ukraine and program committee member and ex-organizer of different Ukrainian conferences. So why we discuss about distributed concurrency primitives? Because if you would like to, in some cases, to build them on your own, or if you would like to use existing concurrency primitives, it will be very nice for you to understand what the problems can be and what you should pay attention for when you are using external platforms. Before we start, let's check what we have traditional concurrency primitives in Java. For example, volatile. Volatile is a very nice keyword that provides us happens before relationship, and this keyword is very utilized in Java internals for building more complex concurrency data structure. Traditional CAS operation that was able to use via unsafe, but now it is only available via atomics. Traditional old-style synchronized block, atomics, locks, semaphores, CountDownLatches, and many others. So that is the Java platform provides us that we can use in a multi-threaded environment. But in a distributed world, in a world of microservices, there are different cases that maybe your microservices would like to access or modify something shared state in also concurrently in a distributed way. And in those cases, you should also able to control how this operation could be executed or not be executed simultaneously by different clients or microservices. For example, if you would like to allow that only one microservice or only one operation could be performed by these microservices, you should use something like mutual exclusion. The same if you would like to read some value from external storage, modify it, and then save it, write it back to this storage, and you should allow that it will be only one microservice, only one client do this. You should also use some logs, distributed logs to do this thing. The same if you would like to limit the number of simultaneous users, connections, and so on, coming from different or coming to different instances of microservices, you could also utilize something like distributed semaphore. Or other cases also that you could imagine or could be useful. To understand how we can move from local concurrency primitives to the distributed concurrency primitives, let's consider how local concurrency primitives, how we can implement the local log behavior, and then we'll try to extend it to the distributed case. So what is the log? Log is used to control access to some shared resource. In general case, in most cases, it is some memory that several threads would like to mutate or modify or read simultaneously. And all these threads, if all threads will access it simultaneously, we will have some inconsistency, concurrency related with concurrency. So we should use some examples or variants of different logs to allow only one thread to access this shared resource. What could be used? Yeah, and only one thread could take this lock, and after this, access to this and modify this memory variable or so on. What kind of locks we can use in a traditional Java approach? The simplest one could be the spin lock or spin loop. For this, to implement this, you can take atomic Boolean. Maybe we can use not even atomic Boolean, but some Boolean variable that will have a volatile modifier, and exclusively change its state from true to false or from false to true. And all other threads will spin on this variable, trying to also atomically change its state to another. If they will not allow to do this, they will continue to wait in a spin loop. So the primitive implementation could look like this. So we have the while loop without anybody, where we can try to execute the CAS operation. Only one thread executed this operation successfully, and all other threads will be running, producing, consume energy, consume your power, electricity, and waiting when this thread will unlock this concurrency variable. This approach has their own benefits. If your lock is very quick and not very long, and there are not a lot of threads, it is even better than, for example, the pessimistic lock. This approach is called optimistic lock. So for pessimistic lock, we could slightly modify the previous solution. We'll also have something like Boolean state that we will modify exclusively via CAS operation. But in addition to the previous behavior, our other threads will not continue to spinning in a loop. They will be parked in a something like internal wait queue, and not will load your CPUs. When the thread will unlock, release the mutex, those threads will be notified by internal Java mechanism, and one of another threads can continue to execute and take this lock. So this is our traditional, how our traditional approach for locking is look like. So what we can do with these two approaches, we can try to do the to go in a naive way and to try to extend it to the distributed cases. So we can wrap this traditional CAS operation or traditional lock implementation in a, for example, a remote procedure call, for example, using gRPC, and expose them externally. So other microservices can use this API and call those locks or this operation externally. So is it possible to do? Yes, it is possible to do it, and it is this very simple way. So we can, in this way, try to implement our distributed lock service. Distributed lock server will run as a separate server and expose such API. And we are moving from threads to microservices. And now microservices can try to take, can use the same approach as traditional threads and perform it in the same way as it was with traditional thread approach. How it could be look like, let's see at the demo. So we can run our gRPC server. It is not interesting how it is implemented. It is only the wrapper of traditional Java data structure. And for CAS operation, we could do the same. So log client is the client for this gRPC API, and log client will perform the same operation, CAS operation. And now I'm printing information who is the owner of this log, and then I sleeping for a while, and then releasing the log. And what we can do, we can try to run those two clients simultaneously and check that only one client will be at the locked state. So let's run client 1, and let's run client 2. Yeah, you can see that this is CAS take by client 1, and there is no information about the second CAS client that takes the log. So after this log is released, the second client could take those logs. So it is a very simple approach, and we could do the same using API for the log. For the log, it even may be simpler. So without any strange loop, while loop, and with traditional log approach. So this is logged by client 1, and no logged from client 2. Okay. Looks very easy, yeah, for the current moment. Yeah, and logged by client 2. So maybe this all for the talk. Yeah, everything is done. Everything was very simple, and we can go to the lunch. But wait, we have a case with a distributed environment. And this distributed environment is completely different than our local environment. What could happen in the distributed environment? In a distributed environment, every remote services can behave in an unpredictable way. That could fail, that could restart it independently each other. The messages or remote calls could be lost, and other bad things could be happened. And in our implementation, let's consider the following scenario. What will happen if the log holder, microservices that is the current log holder, is failed? What will happen in such case? Let's see what will be happened. And for this, let's run the same demo, but in this case, I will kill the log holder. So logged by client 1, and I am killing it. What do you think will happen with the client 2 and with distributed log? Yeah, the answer is it will never can obtain this log, because nobody could tell our distributed concurrency server that the log is released. So this log will be taken by an existing client, an existing microservices forever. Why we don't care about such situation in our traditional local Java case? Because in traditional Java case, we couldn't simply kill the thread. Actually, we do by using stop operations, thread stop operation. Or what could happen with our traditional Java case? It could be deadlocked or live locked, but it is another story. With a distributed case, we should consider and prepare our solution for such scenario that I show you now. In some way, we should be able to detect that the log holder is not anymore active, it is died. How we can do this? We can do this by introducing additional functionality that can be based on heartbeats or lease concept. When the log holder takes the log, when the microservices takes the log, it becomes a log holder, and after this, it should periodically send heartbeats to the distributed server to say that he is alive. If there will be no heartbeats for several seconds or minutes, it depends on your settings, a distributed log server should automatically release the log to not allow that this log will be taken by this client forever. So seems that we have solved the problem. But after we introduce the heartbeats, we introduce another potential problem. So this is related to the false positive detection. For example, what will happen if our network is unstable or our microservice is doing some GC or some another stuff or migrating from one pod to another pod? So in this case, its heartbeats couldn't reach our distributed log server. So our microservice will still alive, but heartbeats could be lost in a network or something else. And after the lease time or the heartbeat, if heartbeat duration is configured incorrectly, the log server could decide to release a log from the live microservice. And after this, another microservice could obtain this log. And we will have the situation when both microservices will have the same, not the same, but will access to the same shared resource simultaneously. What we can do in this case? This case is a tricky case, and it couldn't be solved without participation this distributed shared resource. So when you are talking and when you're considering the distributed log, all components of your system should take participation to provide the guarantees for this log. And to do this, let's discuss the concept of the fenced log. What it is about and what is the fence? Let's consider our initial example. We have a shared resource. We have microservice 1, microservice 2, and we have the log server. When the microservice 1 takes the log, it now obtains not only the log, but it also gets so-called the fence number. This fence number should monotonically increasing, so it shouldn't be a random number, and this number will play a significant role to distinguish the old log holder and the new log holder. So after this, when the microservice 1 obtains this fence, he could access to this resource. But when he accesses this resource, he should include in his request this fence number. In addition to operations that he would like to perform with this resource, he should also include this fence number. And this resource should remember, persist in memory or in a disk, it depends, the number of this fence log. Okay, what will happen next? At next, as we have discussed before, this microservice 1 not able to heartbeat the log server. And at some point of time, log service decided this microservices 1 is not active anymore and release the log from him internally. After this, the microservices 2 could have a chance to obtain this log. And when he obtains this log, it will also have the fence. But as I mentioned before, this fence is a monotonically increasing function. And the fence number will be bigger than the previous fence number. After this, microservices 2 could also access the resource, and resource should check that the number of the fence is equal or larger than known number, than the number that he has seen before. If this number is the same, it will be OK. If the number is bigger, it will replace this fence to the new fence and process the microservice to request. And now, after this, microservice 1 also decided to access this resource because he is still thinking that he is the lock holder. And when he is trying to access this resource, he also includes the fence 1 into his request, and the resource should check the fence number. 1 is less than 2, so this resource should not allow to operation from this microservice 1 should be performed. Only in this way we could implement the distributed lock in a consistent way. There is no other ways to implement the fenced lock. It is your decision, should you use this fence or you will find without it, but in terms of theory, in terms of consistency, it is the only way to do this in a right way. So this was the fenced lock. OK, have we finished? Possibly, but let's think the case we have already considered. We have considered the case when the lock holder, the microservice 1, is restarted, and we, to detect this, we introduce the heartbeats. And to make these heartbeats more reliable, we introduce the fenced lock. But we haven't considered the situation when the lock service is restarted. So what will happen if, for example, microservice 1 takes the lock, but after some moment, the distributed lock server has been restarted. So let's look at the demo, what can happen in this case. So I will run the server. I will run lock 1. I will run lock 2. And after this, I am restarting the server. What you will see? You will see that simultaneously we have 2 lock holders. Because after server is restarted, he doesn't remember who was the lock owner, and the client 1 microservice 1 continue to think that he's owner, but after this distributed lock server has been restarted, it refresh the internal state, and the microservice 2 can obtain this lock. So we have the situation when our 2 microservices take the lock simultaneously. What we can do in this case? In this case, we should provide some availability guarantees for our solution. How we can do this? We can try to replicate our state for distributed lock service so that there will be no single point of failure. We can create a clustered solution for this distributed lock service that will track who and replicate who is the lock owner, which microservices are in a queue, waiting in a queue for the lock services, and if some of these instances of the lock services died or restarted, it shouldn't affect the other microservices or other platform. So how we could implement this distributed replicated lock solution? The only correct way to do this is to utilize some consensus protocol that provide us strong consistency guarantees. In terms of consistency, strong consistency guarantees, it is linearizable. It should linearizable behavior. So it shouldn't depend which member you are asking for. All member should return you the same answer, who is the lock owner. And those consensus protocols also has some could tolerate some members' failure. In most cases, they could tolerate if the minority members failed or restarted. So the majority of members should be active. In general way, consensus protocol is, for example, Raft Paxos, multi-Paxos, and it gives you an ability that collection of machine can perform or work as single coherent groups. And on top of this abstraction, we could implement so-called replicated state machine that provide us strong consistency or linearizable behavior. And allow all these machines in a cluster computate the same state. How it will be computed, I will show you in a few slides. Also, these protocols will allow that some members crash, but it will alive if the majority of members, of the cluster members, will continue to operate. And of course, it plays a significant role in building the reliable distributed system. Okay, what is a replicated state machine and how it works? Replicated state machine consists of several components. It consists of so-called log, replicated log, and so-called state. And clients could send different commands, and these commands will be replicated over these machines. To see how it works, let's look at the example from the beginning. Let's assume that client 1 would like to set Boolean variable to true. For example, take the log. This command will go to the consensus model of one of these instances. If you are taking, for example, Raft protocol, it will be the leader of the Raft protocol. And this command is persisted in a so-called log. But it will not be executed at the current moment. So it will be only saved in this log. You can consider this log as an array of commands. After this, when this command is saved in this log, the consensus module will start replicate this command to the all other instances. All other instances will also persist this command in his log and will not execute it yet. When majority of these members finish with persisting this command in their logs, they can reply to the leader. And the leader will be waiting when the majority of cluster members will respond that they persisted this command in his local logs. When this leader will receive the majority of acknowledgement, what he will do? He can safely execute this command. So only at this moment, when he receives the majority of responses, he started execute this particular command. And after this command execution, for the current example, it will set the Boolean variable to true and could respond to the client that the command has been successfully executed. And also in background, this leader will notify another instances, another cluster members, that they also could execute this command. and because this command is the same, all state machines, all states in all other instances will have the same state. This is, it was a very simple example when we set some value to the variable. But as I said before, we could use any operation, not, for example, set some value. We could use any operation and this operation can be executed in the same way. For example, we can use operation like log operation. So when the client would like to take a log, he produce log operation. This log operation will be saved in those log, will be replicated to in another logs. When the leader will receive the acknowledgement about the majority of operation, it can actually execute this command and perform the log operation. And inside the internal state, he will mark that the client one is the log owner. Yeah. After this, if another clients or microservices would like to also execute this log operation, their operations will be put in something like distributed waiting queue for this log. So, and this queue of weighted members, weighted clients, also will be replicated. The same situation will happen with heartbeats. Yeah. For example, as we discussed before, client or microservice should periodically notify the distributed log service that he is alive. For this reason, he produces heartbeat operations. And about these heartbeat operations, all other instances, copies of these distributed log services should be aware too. Because if this member dies, other members will not know about heartbeats. So heartbeats should also be put in this log, replicated log, and should be processed as another log operation. What this heartbeat operation will do? This heartbeat operation will not change the state, but it can prolong the timer that is set for this log owner. Yeah, so the state is not changed, but the timer after each execution of each heartbeat operation will be prolonged. So that's we should do to implement our log in a consistent way. We have such log and other distributed concurrency primitives implementation in Hazelcast platform. For example, we have atomic long based on the Raft protocol. We have AtomicReference, CountDownLatch, Semaphore, fencing log, as I described it to you. And let me show the example how Hazelcast will behave as a distributed log owner. For this reason, I should start 3 Hazelcast instances. These Hazelcast instances will, okay, I should allow to run multiple copies. Okay, those Hazelcast instances should from the cluster. Yeah, and this cluster will select the leader who will be responsible for, yeah, this is who is the leader, because we will kill them in a few moments. Okay, yeah, I should take the previous, I should take the log to have a leader. Yeah, and in a Hazelcast API, to take a log, you can use the fanced log, and the client will connect to the Hazelcast cluster that I already started, and take the log with name log. After this, I could take the log and receive the fence number that we have discussed before. We will see this fence number in a few minutes. And yeah, let's do this. Okay. Yeah, you could see that the log that this logged by client 1 with fence equal 3. If I started the second Hazelcast client, it will be the same. It will have no be logged owner before the previous client is released. Yes, it is released, and the second client will become the log owner with the fence number greater than the previous fence number. So let's repeat the same experiment that before. When we have 2 clients running, let's now try to kill one of the instances. For example, yeah, this instance. You could see that the number of instances, hope you could see that the number of instances decreased. Yeah, only members, 2 members left. But there will be no problems that that will have 2 log owners. So this will be unlocked by client, logged with client with fence 1. And yeah, it should be, yeah, and it is unlocked. And for the client 2, sorry, yes, it will be locked a little bit later with, yeah, with the fence number, yeah, with the fence number that is bigger. And no simultaneously log hold, we'll have no 2 simultaneous logs holder. So this is for Hazelcast. But this is not the end of this talk. At the end, let's try to think, do we always need a log? Because if you could implement your functionality without pessimistic or optimistic logging, it can be better in terms of performance. To understand what is the performance impact, let's see how we could implement so-called read-modify cycle. Read-modify cycle is when you are reading something variable, putting it into the client, modifying them, and trying to, in atomic way, write it back to the storage where it has been read. To do this, you could use 2 approaches. Yeah? We could take the log, read this variable, modify this variable, and set it back to the storage, and then unlock it. Another approach is using optimistic locking that we also have done before. So we are in a cast loop, trying to modify it until this operation will be successful. What the case is better, it depends. It depends from the size of this object, of this value. It will depend how many clients trying to simultaneously, or microservices trying to simultaneously to modify it. For example, if you have a lot of clients, you will have the worse performance in a cast loop. If your clients is not number is not very big, perhaps this solution will be better than the pessimistic locking approach. But also take into account the following facts. This operation is a remote procedure called RPC. This operation is a remote call. This operation set is also a remote call. This operation is a remote call. And in this case, it looks like only two remote operations, get and compare and set, but the number of those operations in a cast loop can be extremely bigger than in a pessimistic case. So if you have trouble with performance with this solution, you could try to find another better way to do this. The way you could try to do this better is to try to avoid read, modify, write cycle on the client side. So we are taking variable from the server, putting it into the client, modify it into the client, and put it back to the server. Perhaps in our particular situation, we can be able to transfer this modify function to the server. So all modifications related to this read, write, modify cycle will not leave the server and will be executed on the server also in atomic way, but without network latency problem and yeah. So for this reason, in Hazelcast and in other platforms, it is also possible to do, we could implement so-called alter function. Alter function, what it allows to do? It allows you send the body of this function to the server where this variable, where this value, where the modification will be performed. Not any function could be sent remotely, especially if this modify function has some dependency on the client side. But if it is a pure function in terms of client side, it could be easily sent to the client, to the server side. We can compare this behavior with traditional database approach or analogy. For example, if you would like to increment the counter in a database, we could do this way: select count from database, increment the counter, and then trying to update this counter. Yeah. So if the count has not been changed from by another client, we will set a new value of count. Is it work? Yes, it is work, but the performance is much worse than we could perform this in-place modification in a database. The same behavior we could reach using this alter function. It looks like very direct, but we have a customer, very big customer, who had problems with those approaches, and we should educate this customer that he should rewrite the implementation in this way. In terms of performance, this is the difference in performance. This is how many operations could be performed with alter functions. And this is the number of operations that could be performed as a CAS operation. The performance with log is much, in our test, worse than the CAS operation. So the difference in speed is about 3 times. So my takeaways for this talk: if you're able to not use locking, don't use this locking. Yeah, if your solution demands locking behavior, try to use verified approach for this locking behavior. There is a very nice article by Martin Kleppmann about fenced lock. It was a discussion with Redis guys. It is not new, but it is, I think, 7 or even older years old. Yeah, and they found that the Redis log at that times was not consistent. So it is your solution what kind of log you could use, but the only way to reach the consistent available log is to use heartbeats, use fancied log, and if you would like to have the availability, you should replicate your log state. And for replication, you should use some consensus algorithm that is proven, for example, Raft protocol. At this moment, there is all for me. So, thank you. So, questions. Do we have any questions? Room 12. Oh, okay. This is the polls. Okay. Isn't the best locking mechanism the resource access exclusively to only one service responsible for this resource changes? Yeah, if you could implement your system that only one resource could change your resource, yeah, it is the best way. So if your resource could internally control how many simultaneously external clients or services access it, yes, perhaps it will be the best way, but it is not could be implemented in all cases, if I understand this question in the right way. And second question, consensus. Leader asked to the right value, followers asked, then leader answered to the caller, sends the follower right. What happened if the leader would fail between this call? When the leader fail, the Raft protocol or consensus protocol will start a new leader election algorithm. Until the new leader will not be elected, all system will be blocked. So no other operation could be performed. What when a slower microservice asking to a resource is always raised by the fast service with the higher fence number? Will it be somehow blocked, possible indefinitely? Different implementation provides different log. For example, we provide the fairness log. So we, in this case, if you use the fairness log in a traditional, like traditional Java, yeah, it will be the real queue of external clients to take those logs. So in some point of time, it will take the log.